Hello and welcome to the logic of it all. This is our third and final video on logical arguments. In the previous videos, we first introduced two types of arguments where in one type you use the truth table to validate the correctness of an argument, and then in the second one, we only use the syntax of our premises and our conclusion to verify whether an argument is valid or not. We saw some rules of inference in the previous video. In this video, we are going to see more of those, and also we are going to look at some examples where we use a combination of different rules of inference to complete a proof. So the first rule that we are going to investigate in this video is OR introduction. So if you remember, the formula or formulas on top of the horizontal line, in this case we have only one, is the premises that we have. So in this case, we have only one premise, which is P. And then the formula below the horizontal line is the conclusion. So basically, the way that we should interpret this rule is if we know P, if we know that P is true, then it follows that P or Q must be true as well. So P or Q can be derived from P. And because we are introducing this OR connective in the conclusion, this rule is called OR introduction. And similarly, if we know Q, from that we can infer P or Q as well. So that's another version of the OR introduction rule. Now here's an example. We have one premise, which is P and Q. That's the only premise that we have. And we want to show that from that we can infer P or Q. Okay, so if you remember, we start by listing our premises. In this case, we have only one, P and Q, so that's my premise. Then, after listing all the premises, we apply the rules of inference to the previous lines to get new formulas out of the known ones, out of the ones that we either assume to be true or know to be true. Now, what I can do here is that I can use AND elimination to get P from P or Q. So I can infer P from P and Q. So from line 1 using AND elimination. Because remember from the previous videos that AND elimination says from P and Q you can infer P and also you can infer Q. Now in the next line I could infer Q as well, but if you look at OR introduction, knowing either P or Q is enough to infer P or Q. So right here, I can infer P or Q from line number 2 by using OR introduction. Because OR introduction says if you know either P or Q, you don't need to know them both. If you have one of them as your premise, you can infer the disjunction P or Q. And that's the end of the proof, because remember the proof is complete if we have the conclusion listed as one of the known facts or statements. Now, the system to be complete, there are other rules that we are not going to investigate in detail here. But here is a list of some of other inference rules that we didn't cover. So we have OR elimination. In general, the way that you should think about this is for each one of these connectives and or negation, implication, there is an elimination rule and an introduction rule. So in the previous slide, we saw AND introduction. This is, OR introduction. This is OR elimination. And also we have excluded middle, which says without any assumption, you can always infer P or not P. And also from falsehood, everything follows. So if you have falsehood as part of your premises, then you can infer any proposition that you like. And there is OR introduction as well, and so on. Now, what we introduced here in this series of videos is a simple and restricted version of what's called natural deduction. It's a system of deducing new propositions from known ones. And usually for a system like that, for a proof system, there are two properties that we are interested to know whether the system has those. And ideally, we want the system to have both these properties. And basically they're called soundness and completeness. Now, soundness means anything that can be proved using the rules of inference has to be true. So nothing that is not true can be proved in the system. So obviously this is something that you want, because otherwise the system, if you can prove false statements in your system, obviously that's not a good proof system. So soundness guarantees that. And on the other hand, ideally we want our set of inference rules to be complete, which means that any statement that is true, any propositional formula that is true, should be provable in the system. Okay, so that's called completeness, which means we can prove every true statement in propositional logic using our rules. And then on the other hand, soundness means we cannot prove anything beyond that. We cannot prove anything that is not true. Anything that is false shouldn't have a proof. So that's soundness. And as I said, this system that we introduce here is the subsystem, if we include all the other rules of inference that we didn't go into detail, is a system called, is a version of a system called natural deduction. And it has been proved that natural deduction is both sound and complete. So you can prove anything that is true in propositional logic using the rules of inference in natural deduction, and anything that you can prove has to be true. In other words, you cannot prove anything that is not true. And both these proofs are not trivial, and there are proof systems in, if you go higher than propositional logic, there are systems that, for example, we can prove soundness, but completeness cannot be proved as well. So these are cases where the system is more complex than just propositional logic. Now, to wrap this topic up, we are going to see a couple of examples where we get to use a combination of different rules to complete the proof. The previous examples were specifically designed so that we focus only on one rule of inference. Now, in these examples, we try to combine them in different ways. So here's the first example. We have three premises, as you can see. So the first premise is this implication here. Then if P, then Q is the second premise, and P is the final premise. And obviously our conclusion is R. So we start by listing our premises. We have three of those. And we always have one eye on the conclusion, because it could be that there are different ways that we can apply our rules of inference and get new propositions. But we should always keep in mind that the goal is to reach to the conclusion, in this case, R. So somewhere down the line here, ideally, I want to reach to R to complete the proof. Now, immediately you can see that from line 2 and 3, we can apply arrow elimination here from P and Q. If P then Q and P, we can get Q. So from 2 and 3 with arrow elimination, we get Q. Now, we want R, and the only place that R appears is here. So somehow we need to use arrow elimination to get R out of this. But to be able to do that, I need P and Q. Now I have P on line number 3 and Q on line number 4. So using these two known facts and the inference rule for AND introduction, I can get P and Q. So from 3 and 4 using AND introduction. And now if you look at line number 1 and line number 5, I have if P and Q then R. Line number 5, I have P and Q. So combining these two using arrow elimination, I can get R, and that's the end of my proof. Now here's another example. Again, I have two premises. Q and S is the first, and then if P or Q, then R is the second. And what I want to prove from these two hypotheses is S and R. So again, first line, second line, I list my premises. Now, I need to see which rules, which inference rules are applicable at this point. The only one that seems to be applicable is using AND elimination on line number 1. So we can get Q from line number 1 using AND elimination. Now we can use Q to infer P or Q using OR introduction. So from Q, which is line number 3 here, with OR introduction from Q, we can infer P or Q. Now, you might say, why P or Q? Because P or Q is here, and if I have P or Q, then from line number 4 and 2, using arrow elimination, I can get R. And that's exactly what we do on the next line. So from 2 and 4, using arrow elimination, we infer R. Now, our goal is to prove S and R. I have half of it at the moment. I have R here. Now somehow I need to get S. And again, if we look at line number 1, I have Q and S. So from that, using AND elimination, I can get S. So from 1 with AND elimination. And now that I know R and I know S on line 5 and 6, I can combine them using AND introduction to get S and R, which is the conclusion I was looking for. And that completes the proof. And finally, our last example. It's a little bit more complex, this one. We have hypothesis number 1, hypothesis number 2, 3, and 4. And from these 4, we want to see if we are able to infer not Q. So let's list our premises first. We have 4 of them. Now you need to look at your premises and also have your inference rules ready and in front of you and see what can be done here. But the first thing that we can do is, if you look at the first line and the fourth line, using backward arrow elimination, line number 4 says if R then P. Line number 1 says it's not the case that P, then it cannot be the case that R. So we can infer not R from 1 and 4 using backward arrow elimination. The next step, we can combine 5, which is not R, with 2, which is S. So we have S, we have not R. We can use AND introduction to get not R and S from 5 and 2. Now, again, if you take a look, this matched perfectly with line number 3, because we have not R and S. Line number 3 says not R and S implies not Q. So using arrow elimination with line 3 and 6 gives us not Q. And that's exactly what we wanted as our final conclusion. So that completes the proof.